Hello, my name is Guy Aros. I'm a 3D printing application engineer working at Systematics. Today in this presentation, I'm about to speak about innovation in mechanical design using guidelines and optimization tools for additive manufacturing. So let's begin. Generally, in mechanical design, we design the parts according to the manufacturing process, because every manufacturing process has its own limitation. For a single part that has the same purpose, it will be designed very different according to the manufacturing technology. For example, if we choose to manufacture this part using sheet metal, it will look very different compared to a part that will be manufactured using CNC milling. Moreover, even the CAD softwares that we use are built in a way of thinking guided by the manufacturing process. The features we use in the CAD software are directly related to the techniques and technology that eventually used for manufacturing. So the same concept is also applied when we seek to manufacture parts using AM technologies. It means that in early stage of part design, we need to consider the manufacturing process and to design the part accordingly. So far, nothing is new. As a mechanical engineers, this should be our normal design approach. Although it's not always the case. In many cases that I have encountered, designers would simply seek to print the same part geometry as they plan to manufacture using the conventional methods. This is why I think it's important to discuss about design for additive manufacturing. So, what is design for additive manufacturing? It's a design methodology that focuses on optimizing the design of a product to be manufactured using AM technologies, while leveraging the AM capabilities, which allows high degree of design freedom. While AM is continuously becoming inroads into mainstream of manufacturing, we must be aware of its limitation and capabilities in order to design high-performance parts efficiently. So, why it is important to use DfAM approach? When using DfAM, we will get better parts in terms of functionality, reduced weight, and increased mechanical properties, while also reducing cost and lead time. Reducing cost by minimizing material usage and in some cases reducing post-process time. We are familiar with the plot of parts cost versus quantity, and we know that for small to medium batches, additive manufacturing can be very economical. For many years, the cost of part that was manufactured using AM has been considered as a flat line, which means that the first part can cost the same as the 1000 part, which would cost the same as the 10,000 part. The main negative assumption of flatline curve is that you can go from design to manufacture without any development or setup cost. The truth is that any process will need some sort of development phase in order to meet the quality requirements of the design. During the development phase, both the design and process will always require some tuning. The designer tunes the design to the final fabrication process, and the process engineer tunes the process to the design and its requirements. The beauty of this tuning for AM or digital fabrication is that the tuning can be done digitally and no expensive tooling or expensive reworks are needed. So how can we optimize AM by using the DfAM approach? Due to the limited time of this presentation, I am unable to go into deep dive about DfAM concepts, but I will try to cover the general rules and principles which stand behind it. The first subject is that we must know the capabilities of the equipment we are using for AM. Usually, equipment manufacturers publish a document that describes the performance envelope of the equipment. These documents usually refer as design guide. because it contains important information that the designer should consider. It usually contains information such as maximum and minimum part size, minimum features that can be printed, such as hole diameter, pins diameter, wall thickness, and embossed, debossed features. Also, overhang information and some general best practices. If we want to make the best out of the equipment, we need to be aware of this information. It is also important to take into consideration the part loading condition while in use. In some AM technologies, actually in most of the cases, part properties are anisotropic, meaning that the properties of the part such as strength, elasticity, durability, and accuracy, to name some of them, are not the same in all directions. So while designing the part, we need to consider how it would be oriented inside the build chamber, and we should alter the design accordingly. For example, for snap fit features, we would like the forces to act in parallel to the layer lines and not in perpendicular. For technologies that suffer more from anisotropic properties and delamination failures, such as FDM, we would consider to strengthen the part by implementing hardware that will take the stresses away from splitting between the layers. This has a drastic influence about how to design the part for AM, and in some cases it may be even necessary to split the part. Another consideration in DfAM concept is to minimize printing supports, which are often necessary in some AM technology and definitely existing in common one. Supports are waste of material and also time consuming, twice, one on the print time and the other in the post-process time. The goal is to minimize the supports required for a print job. We can achieve that by designing a gradual transition from bottom to the top of the part. For example, a circular hole, which normally is sketched as a circle, we can sketch it as a teardrop shape and thus creating a gradual closing of the whole top surface. It is also very good practice not just for holes, but for internal channels which are often difficult or impossible to extract the support material out of it. We can also fillet or chamfer edges to improve overhang, and add draft angles to provide a gradual transition from down to top. Structural and fluid generative design is a powerful approach that goes along DfAM. Structural generative design uses algorithms to create optimal part geometries that are strong and lightweight. By inputting design constraints such as load, boundary condition, and material properties, the software generates a design that is optimized for the specific application. This approach can lead to parts with complex geometries that are difficult to produce using traditional manufacturing techniques. These parts can be manufactured using AM with minimal supports and can be lighter and stronger than parts that produced using conventional manufacturing. Topology optimization is another powerful technique for DfAM that uses computational method to generate optimal part design. This technique starts with a virtual model of the part and then using algorithms to determine the optimal distribution of material within the design. This advanced simulation tool can be used altogether to optimize part geometry for specific requirements to create a part that can perform the function of multi-components. In some cases, it may be possible to integrate features such as fastener, hinges, or snaps into the part geometry, eliminating the need for separate components. This approach can help reduce assembly time and cost, simplify the supply chain, and improve overall part performance. In this example of bike wheel assembly, using advanced simulation tools, it was able to reduce the number of components from 4 to single component and achieving a weight reduction of 52%. Obviously, this part is very difficult to manufacture in conventional methods, but can be manufactured using AM technologies. DfAM can also be used to create complex parts with moving mechanism. They can be printed as a single part with each link connected by a flexible joint that allows for relative movement. These parts can be used in a wide range of applications, from robotics to fabric design. Chains, fabrics, grippers, gears, CV joint, passcodes, sliders are just some of the examples. Springs can also be printed with different shapes and design used to achieve specific performance characteristics. By optimizing the design of the spring, it is possible to create specific spring constant and other properties such as progressive springs and even dampers. Hinges can be printed with different design used to achieve specific performance and range of motion and torque resistance. Snap-fit connections are a particularly good design method for AM because they can be integrated into as the part and overall increase part performance, eliminating the need for additional fastener or adhesive. This can help to simplify the manufacturing process, reduce number of components needed, and improve overall quality and reliability of the finished part. Lattice structures are a type of porous structures that can be created by AM. Lattice structures are composed of repeating unit cells that are interconnected to create a three-dimensional network. These structures can be designed to have specific mechanical, thermal, or acoustic properties. Lattice structures can be designed to have a range of properties, including stiffness, strength, and density. By varying the geometry of the unit cell, it is possible to create structures that are optimized for specific application. For example, a lattice structure can be designed to be stiffer in one direction than another, or to be more flexible in certain regions of the part. Partial infill is a technique used in additive manufacturing, mainly in FDM, where only a portion of the internal volume of the part is filled with material. This is in contrast to solid infill. Different types of infill patterns can be used, such as grid, triangular, honeycomb, and gyroid. One of the benefits of partial infill is that it can significantly reduce the amount of material used in the manufacturing process, leading to a cost saving and reduced material waste. It can also lead to improved part performance by allowing for more optimized distribution of material within the part, and thus reduce thermal issues during the print process. An interesting fact is that for internal ribs that normally considered as good design approach to reduce weight are not that optimal for technology that uses partial infill, because sometimes they can lead to increase in print time and material usage. Another key consideration for DfAM is the post-process phase, which occurs after the print job in some technologies. When designing a part for additive manufacturing, it is important to consider the post-processing steps required to achieve the desired surface finish, dimensional accuracy, and mechanical properties. For example, for powder-based technologies, it is important to design for depowdering. Depowdering refers to the process of removing excess powder from an additively manufactured part after it has been printed. When designing a part for depowdering, it is important to consider the accessibility of the powder trapped inside the part. The design of the part should be such that it minimizes the retention of excess powder. This can be achieved by incorporating features such as angled surfaces or tapered walls to encourage the powder to flow out of the part more easily. Another important design aspect is the implementation of hardware. Dowel pins used for accuracy positioning and to provide hardened steel wear surfaces for the areas of the parts that interact with abrasive surfaces. Metal threads inserts allow for strong and durable bolts connections, and bushing or sleeves bearing provide high cylindrical precision and smooth concentric clearance fits, also distributing the load to the part with a larger surface area. Incorporating additive manufacturing into end-use applications require total confidence in part mechanical properties. Today, there are simulation tools that allow to deliver trusted parts faster while reducing design print test iteration. Markforged Simulation is an example for simulation tool that enables virtual testing of FFF parts. After identifying anchors and load surfaces of the part, entering the value for loads, factor of safety, and max deflection, we can run a simulation that confirms whether the part passes or failed. Moreover, using optimizer function, the simulation runs multiple times that generates print configuration that prioritize faster print time or less material, while ensuring performance required as satisfied. Using print process simulation tools enable us to validate part performance and optimize print settings to ensure the part meets the performance requirements while maximizing manufacturing efficiency. Using Markforged fiber reinforcement allow to produce parts with reinforced composite materials, providing additional strength and durability with high strength-to-weight ratio, which in some cases can be alternative for metal parts. The fiber reinforcement technology involves the use of continuous fiber, where fibers such as carbon fiber or fiberglass are integrated into the part during the printing process. The fibers are placed in strategic places within the printed part, providing strength and stiffness in specific direction, similar to how fibers are used in composite materials. Using unique advantages of composites, engineers can employ different tactics to strengthen specific areas, reinforce certain part sections, or control fiber placement. Thank you very much.